And we're going to talk about how to speed up VHDL verification significantly by making a better test bench architecture. But before that, just want to introduce, yeah, so let's think. You need to push the, yeah, good, thanks. Briefly mention that I come from a company called EmLogic, which is an independent design center based in Norway, doing embedded systems and FPGA. Established only 2.5 years ago, so we had a huge ramp up to 35 people now, and 15 people, actually, well, 14 it says, actually 15 on FPGA. And we continued legacy from a company called Bitvis that was quite leading in Scandinavia a few years ago. We also have a verification IP methodology provider via the UVVM, which I'm going to talk about in this presentation. Also do design courses and on verification and design. And about myself, I've been in the business for almost 30 years, or more than 30 years. Graduated from University of Glasgow many years ago, and also worked with the Philips semiconductors in Switzerland on ASIC design, and on lots of different companies in Norway, both on ASIC and on FPGA design. I've been working on methodology improvement for quite a few years now. So, what is UVVM? It's Universal VHDL Verification Methodology. So it's basically UVM with the VHDL in there. It's a library and methodology. It's free and open source, can be used for FPGA, ASIC, CPM, CPLD. It's mainly used for FPGA. It gives a very, it's a very structured, gives a very structured infrastructure and architecture, and it definitely improves verification efficiently, significantly, and at the same time also improve the quality. Recommended by DUTs for test bench architecture. ESA projects, we have run several ESA projects, I'll come back to that in a moment, to extend the functionality of the tool. And it's available on GitHub and also on IEEE open source. And it can run on any VHDL 2008 compliant simulator. So I guess you've seen this figure from time to time from the Wilson Research Group, saying that around 50% of the development time is spent on verification. And the question I would raise is, could this time be reduced without reducing quality? Then if you look at verification time, then you see that half of the verification time is actually spent on debugging. That's debugging the test bench, debugging the design itself, and complete environment. And in my head, I think we can definitely be more efficient. I'll come back to that, of course, as well. So the main challenges beyond sort of basic verification, well, what everybody talks about is, of course, randomization and functional coverage. I don't need to talk about that because everybody does that. Then quite a few talk about specification coverage. That's important. Very few talk about how to handle lots of different interfaces at the same time. And almost nobody talk about cycle-related corner cases, which I think are quite important to be aware of. I'm going to talk about more about that. So this is basically a decreasing awareness and increasing problem. So what enables quality and efficiency? I think that's important to be sort of aware of and consider. One of the most important things is overview and readability. Pretty obvious. Modifiability and maintainability. We talked about debuggability and, of course, also reusability. These are extremely important for both quality and efficiency. And in order to get this, you have to have a good structure and a good architecture. But that's not enough by itself. You also have to focus on simplicity. You have to make things as simple as possible, but you have to sort of find out which parts of the design are most important for simplicity, because you cannot have simplicity everywhere. And this is basically what we target with UVVM. This is an overview of all the parts of UVVM, and I'll come back to some of these later on. So before I start going into the sort of more complex parts, let's look at the simple part first, the entry part, entry level. This is an example of a test sequencer code for a dead simple interrupt controller with clock reset, a simple bus interface. That's basically the simplest possible interface you can imagine, with just data, address, read and write, and so on. Then n interrupt sources and the resulting interrupt to the CPU. Make a test bench around that. The first thing you need, of course, is to have a clock generator. And from the utility library in UVVM, you just pick basically a procedure and instantiate that procedure directly in your architecture. And it's a concurrent procedure. It works exactly as a process. That's all you have to do to actually generate that. And you can, of course, use more advanced versions of that clock generator with enable signal and so on. Then, of course, you have the test sequencer that's going to do the whole job of verifying that interrupt controller. And I'm just going to show you some important commands here at the base level. So you have a log command, different forms. This one is using an ID called ID log header, which also ID is here used for verbosity control. So you can use different IDs to include or basically filter out different messages. And this ID log header also have the extra capability that it allows you to format the output like a header. So that's the transcript from this command. Then, and by the way, this is a simplified transcript because it will be too wide for the screen to show everything. And then you would check value, because that's basically the thing you do always in a test bench. Checking different values to check that the interrupt to the CPU is 0. And then with a message, a mandatory message, because we want to provide the big M in methodology as compared to what was mentioned as small m in the previous presentation here. So we want to provide a methodology where we sort of force the designers to do things the right way. And then there should be a message there. You could, of course, just leave it open and not put in anything in there, but I think it's very good to have a message, because then you get it in the transcript as well. You can check for stability. That's important as well. So rather than checking and sampling this interrupt to the CPU, checking that it's always 0, you check that it has been stable for a given time, from now back to reset time, for instance, in this case. And then you get a log for that as well. Now, of course, you generate pulses. In this case, on interrupts, generate a pulse on interrupt to the source, set it to 1 for 1 clock period. And that is also put into the log. And what is really important in any test bench is to make sure that when you wait for something, you must always wait with a timeout. So this await value says wait for interrupt to the CPU to go to 1 at the earliest after 0 nanoseconds, at the latest after 2 clock periods, because there's an interrupt expected. And then you have a message saying what you did. And then just an example also of a BFM, bus functional model, to show just how you can write to this simple bus interface just by an SPI write with the address and the data, and again, a message. So that's the complete thing. And all these procedures are with a positive acknowledge, because it's important to debug your test bench. But if you only want them. So that means after a while, when you know everything is working, you're doing regressions, for instance, you can basically remove most of these messages via verbosity control. And of course, there will be a mismatch report. I'll come back to that later on as well. Alert counting and so on. So these are some of the other commands that we use for in this utility library, sort of basic version. I'm not going to go through that, but you can see that you have lots of different commands that can be very useful for any type of test bench. Then going one step up to communication interfaces, where we have bus functional models. So with this utility library, we also provide some BFMs. In this case, for UART, so you use a bus functional model to write into the RX and to read data out of the TX, and also to write and read via this simple bus interface. So the command is that simple: it's a UART transmit and the data. And of course, data is coming into the UART. So sometime later, you want to check that it's available in the RX register. You just do an SPI check and check that you get the right results. Then in the transcript, you'll see that you did a transmit and you did a check. Everything's okay. Similar on the TX output. This case, of course, you write the TX register, and then sometime later you expect data to come out on the TX from the device in the test. And in this case, we're just showing a case where SPI write was okay, but the expected data was wrong. So basically what you get is a mismatch report like this, that where the value was so-and-so, whereas we expected something else. And there's free and open source BFMs for lots of different interfaces. So all these, you can get full BFMs like this for all interfaces. And open source, of course, means that all the code, you have access to the RTL of the code. So, but BFM procedures are not sufficient. They are great for simple usage. They are dedicated procedures in a simple package. You can just reference them and call them the process. That's simple. Everybody understands it. But the problem is that the process can only do one thing at any time. So that means it can either execute that BFM, another BFM, or do something else. It cannot do more things at the same time. So to do more than one thing, we need multiple processes, multiple threads, basically. And the sort of normal way of organizing that is to put these processes in an entity or component in order to be able to reuse that in a sensible manner later on. Okay, I'll come back later on. So we're talking about simultaneous activity here on multiple interfaces. That, of course, applies to the UART case we saw with 3 interfaces. Lots of other, or most other interfaces as well. Maybe not the interrupt controller, because there's not that much sort of relation between the different interfaces on the interrupt controller as you have on, for instance, a communication protocol like the UART or more advanced stuff, or even the FPGA with multiple interfaces. And it's not acceptable to handle only one interface at a time, which is done in many test cases. They handle just write one interface, and then later on they read the result out of that interface. But then you're not doing anything in parallel. And of course, parallelism is where we tend to make our bugs. So, yeah, so handling interfaces via parallel processes, that is possible, of course. But we need to align actions on multiple interfaces, make sure that we skew one interface access with respect to another to make sure we hit the corner cases. And this is comparable to aligning tightly coupled software that is split on multiple CPUs, and you have to always synchronize and align that software, and that's really complex. And this also applies to a really simple UART, as in this case. UART is considered extremely simple, but it does have this problem. So we need tight control on one interface with respect to another to hit the corner cases. And then when I talk about corner cases here, I'm talking about cycle-ready corner cases. So I should probably sort of explain what I mean. I talked about this for 10 minutes, I think, in the last verification futures. So cycle-ready corner cases occur when the cycle in which an event happened is not fixed, and this event is related to another event, fixed or not. I.e., if it was fixed, it wouldn't be a problem, because then that would always happen. So the problem here is that if you don't know when something is going to happen on one interface with respect to another, that's when you have a potential cycle-related corner case. Yeah, so typically it could be events in different state machines that affect each other or affect the same object. It could be any 2 or more events combining into state machine, interrupt controller or DMA, for instance, receiving 2 triggers n cycles apart. What happens then? Or any communication interface, as in any, where you have a readout at the same time as you have new data entry, and lots of other scenarios as well. So let's look at an example here. To illustrate this, this is VHDL code and pseudocode. So basically what it says is if RX data register is read from the CPU, then you do something. Else, if a new byte is received from RX, then you do something. Right, so this will be a bug if this something is to go to a new state or to assign something to the same object if it happens in the same cycle. Because then basically that would override that, because that if will trigger and the else if, even if it's true, will not happen. And then people say, well, this is obvious. I wouldn't code like this. Well, people do. But even worse, I mean, is that people often have a different kind of coding style where this is not so obvious. As in this case, where you have exactly the same functionality, but you have the if statement one place in your code, maybe 10, 50, 100 lines of that code, and then you continue doing something on this stuff. And that will, of course, not be that easy to actually see that you have this potential conflict. This is something that happens in lots of projects and is a huge problem, actually. So how huge is this problem? Well, if you look at a clock of 100 megahertz and a bit rate of 100 kilohertz, this is getting detailed, but then you have a byte frequency of 10 kilohertz. So a probability of having a bug will be 1 to 10,000 per byte, right? Probability of detection in a sequential simulation for one single byte is then, of course, 1 to 10,000, right? It's that simple. For thousands of bytes, it would still be almost 1 to 10,000 in most test benches, or at least in lots of test benches. People think that now if I write 1 million bytes, then I'm going to hit this. No, because you're doing the same thing over and over again with the same kind of structure and the same distance between your writes and your reads. And maybe slightly more than 1 to 10,000 in a few test benches, but not necessarily much better than that. And probability of detection in the lab, well, totally depends on the setup in the lab. But for lab tests, we tend to do the same thing. We do things in sequence, ordered sequences, and we tend to maybe have, well, maybe 1 to 1,000, but still a very, very small chance of detecting this problem. And of course, in real life, things are going to be random on these two interfaces, so you're going to hit this problem, and it's going to be buggy. So how do we avoid corner cases? Well, most corner cases are given by specification, and they cannot be avoided. They are there, of course, unless you can modify the specification, but there are always going to be some corner cases. And the corner case in itself is not a problem. It's only a problem if you cannot check for that corner case, detect the corner case, and check that everything is working correctly. So let's look at that detection, for instance, for this communication interface example. First of all, awareness experience is extremely important, but the awareness about this problem is generally very low. So most designers will miss this box. Simulation may detect everything if you do it the right way. So experience is important, and the approach definitely matters a lot. Oops, sorry. Yeah. We need a good test bench architecture that allows us to skew one interface with respect to another to actually hit these corner cases. Review is, of course, very important here. Review can definitely detect these types of problems if you are aware that this is a problem. Lab tests, I mentioned that already. It's often restricted also by the competence of the people doing the lab tests, because they might not even know it is a problem in the first place. And it's often restricted by the application or test software. So basically, simulation is definitely the best way of detecting this and handling this. So how do we do that? We just concluded that these BFMs are not sufficient. We need an entity where we can have multiple processes so we can handle these interfaces individually and independently. So for that, we need an entity, a component, a verification component, and we call it a VHDL verification component and call it a VVC. So what is the VVC? Well, VVC will then be something you put in between the test case sequencer and the device on the test. So rather than the test sequence just calling a BFM, it's now using verification components. Looks like this. You first have an interpreter, and a command queue, and an executor. The interpreter will look at the command from the test sequence and look at, is this command for me? If so, is it to be put on the queue for execution? Or otherwise, if not, then I'll just case on what to do, like for instance, flush the queue or set up something or whatever. Comes through the queue, and the executor sees there's something on the queue, will fetch that from the queue, and case on what to do. In this case, is it a read, is it a write, is it a check? And then it will execute the relevant BFM towards the device on the test. So basically what you've done is just to distribute the execution of the BFM into this verification component rather than the test sequence doing that job itself. So what is the transition here? That's a BFM test bench. So how is this handled with verification components? Well, this is the equivalent test bench with verification components. So you can see that we have added verification components on every single interface. And what would the commands look like? Basically exactly the same. With one exception, we've added a parameter or parameter set saying that this SPR write with this address and this data is now going to be distributed to the SPI verification component instance number 1. So that basically says, take this SPR write, but don't execute it yourself, because that would be that command. But in this case, it will just be shifted or given to this verification component so that can execute this command. But of course, on the interface here, they will be using the BFFs, as I showed in the previous case. And the verification components also include important things like delay insertion. I'll come back to that. Command queuing, completion detection, activity registration, and lots of other functionality that you can put into a reusable verification component to make that far more valuable. So let's look at the verification approach for cycloidal corner cases. So as I said, we have to skew one interface with respect to another. That's in order to actually reach these corner cases. So we have the UART transmit, and we have the SPI check. So 2 commands we're going to use on the interface up there, right? And we're going to check, are there any problems on the design here with respect to these cycloidal corner cases. So these happen at the same time because the sequencer issues this command and it's sent immediately directly to the UART verification component, 0 time, only delta cycles. And then immediately after that, after just a few delta cycles, it will send this command to the SPI verification component. These commands are distributed to all verification components needed simultaneously. That means they can all start simultaneously as well. And the sequencer is free to do something else. And then in order to actually skew this with respect to each other, we can do this insert delay on the SPI verification component with, in this case, the UART frame time plus a number of clock periods. So we're delaying, basically that is going into the queue of the SPI verification component. It sees that it first has to insert a delay before it is allowed to do the SPI check. That means we have now skewed those far apart. Yeah, and what we also have at the end here is something called await completion. That is the synchronizing mechanism here. That allows us to say that at this stage, this happens at the same at one time, same time, because they're just distributed. And this command allows the simulation to run because now it says, hey, wait now until the UART verification component number 1 is finished. So that means it waits for this command to be executed. And then we just run a loop around this and doing this from C cycles before an assumed corner case to C cycles after the assumed corner case. And why is that? That's because we have a suspicion as to where the corner case is. But then we don't know exactly how many clock cycles are used in the pipeline for the UART RX receiver or for the CPU access. So since we don't know that, it's approximately there, but to make sure we will hit that corner case, let's start 10 cycles before that and skew our way all the way to 10 cycles after that. And we have covered the whole situation with 20 runs, and we know we're going to hit the corner case. So that will hit the corner case within a few iterations. Okay, so now we have these verification components, which are going up in the sort of complexity here. Because these verification components are easy to extend, we can add more stuff to that. We can add local sequencers, as in not just having just a check, a read, and a write, but can actually have a write 100 or n bytes with random data, for instance. It's easy to add that type of command as well. It's easy to add checkers and monitors, whatever, inside the verification component, adding to the value of that verification component. It's easy to handle split transactions because we have a system that's very structured. We have an interpreter, a command queue, an executor. We can just repeat that structure. And then we can use this executor for a read request, for instance, to Avalon. And then once the read request is sent out to the Avalon interface, we pass it on to the FIFO, the command itself. Then the response executor, which will be doing the read response. Did I say read request from here? And then this will just respond on the slave, the interface, and see that data is available. And it will then execute the read response. While this is executing the read response, there might have been lots of read requests in the meantime. With this structure, it's dead simple to make that kind of handling of the interface, which normally leads to chaos in most test benches. And it's also easy to handle out of order execution by just not having a FIFO there, but a queue there. Okay, let's look at some VVC-based test benches. Here is an example of an axis stream. The device in the test just has an axis stream slave, FIFO, and a master. And it's connected with some verification components, an axis stream master on this side, slave on this side, clock generator. And as you can see here, the first thing that happens is an axis stream transmitting into this verification component, basically just distributing the command to the verification component, and at the same time also distributing a command to the slave over here, so that now we have set up the system. Then this will start pushing data through the system into the slave over there, which will then expect this data and scream out if this is not correct. So this device in the test is typically VHDL, but of course the device in this test could be Verilog as well. There's no problem doing a mix of languages here. It's a Lego-like test harness. Anyone can understand this because it is really dead simple to understand. You have replication components and a test sequencer. And even a software or hardware developer could write the test cases. It's really sort of, from them, it's, I would say, quite easy to understand what's happening inside the test bench. And if you have interface changes, you wouldn't have an axis stream, of course. Oh, you could, because you could suddenly start to use more of the axis stream protocol. Then there wouldn't be any change anywhere apart from the fact that you would connect this with some more signals. So the test sequencer wouldn't be affected at all. And all verification components could be controlled from one single test sequencer. And that's the beauty of this, because that means you have control. You can see every single thing that happens in your system from just reading one single process. If you want to, you can have multiple sequencers as well. But again, back to the thing with the multiple CPU cores, it's difficult to follow, it's difficult to see what's happening in the system. So trying to make it with one central sequencer allows you to have much more control of your system. So And multiple advantages of using verification components. It's simultaneous activity on multiple interfaces. That's the obvious one. Some of the ones I mentioned a bit almost already. Some things are unique to UVM. You have full control and can align all verification components from one single sequencer. You can insert delay between commands to skew them with respect to each other. And some other stuff as well. Well, I mentioned them. You have simple handling of split transactions. I mentioned that. You have common commands to control different things. Same commands from one VSD to another. Simple synchronization, and you can also have broadcast and multicast to all the verification components. That means you have a better overview, better maintenance, accessibility, and reuse. Again, lots of free verification components as well. So for the same basically as for the BFMs, it's the largest collection of VHDL interface models available, free, that should be free and open source VHDL interface models. And they contain, lots of good functionality, well documented, and also have example test benches for every single one. We have cooperated a lot with ESA, the European Space Agency. We had one project 2017 to 19 where we did all these extensions, and I'm going to just briefly touch on two of those, two of the most important ones, scoreboard and specification coverage. So this is the case we had with the axis stream test bench. So now I'm going to just introduce scoreboards as well into this test bench. So we have an axis stream scoreboard here. I'm just going to show you how we use that. Again, we'll have the axis stream transmit, telling this VOC to transmit data into the device in the test. Again, we have a command telling the axis stream slave verification component, in this case, not to expect data or check it, but just to receive it. And then data here will be given out, or actually rather fetched by the model. This verification components, all verification components provide an interface to the external world saying exactly what they're going to do on that interface. So this model will just look at that interface and see what's going to happen there, and then generate the expected data to the scoreboard. Of course, in this case, it's a one-to-one, so it's that simple, but it could also be more complex. Then data will pass through, reach the axis stream slave VOC. And as I said, that was just a receive, so just receive it. It will provide it on the interface, so it's available from the outside. And that can then be provided to the scoreboard. And the scoreboard will now see the expected data and the actual data and match that, hopefully. Or otherwise, it will give you a mismatch report. So what does the scoreboard look like? It's basically just a comparator. You're comparing expected data against actual data, and you generate lots of statistics. And this could be any generic data type like standard vector, integer, or any type of record. And you could do insert, delete, fetch, and lots of things that you can do on any general queue. So basically lots of different queue operations. And you can generate lots of statistics, like counting number of entered elements, pending, matched, mismatched, and so on. Then there's a lot of extra commands to do logging, flushing the queue, clearing statistics, and so on. And also very important is that we also have a configuration record that allows us to specify whether we should allow data to be lost, whether we should allow to have out of order data, because this is something we need to specify, because if data comes out of order and when that isn't specified, then that's a bug, right? So we need to specify that. Okay, let's jump to specification coverage. So that is basically something we do in order to assure that all the requirements have been verified. So we need to specify all the requirements up front. This is just an example from a motor controller showing you 4 potential requirements. Of course, there would be hundreds of requirements, but I want to simplify this. Then we want to report coverage from the test sequences, from the test bench, to make sure that we report everything that happens in there when we actually test some of the requirements. Then we generate a summary report, and the summary report will give us different types of summaries. So it could be coverage per requirement, it could be test cases covering each requirement, and also requirements covered by each test case. This is what's called requirements traceability matrix. Basically, see this in different ways. And this can be accumulated over multiple test cases, of course. And this requirements traceability matrix is something that's mandatory for safety and mission critical projects. And ESA, for instance, is very clear that this is mandatory for their projects. And yes, safety is even more important. I would say it's strongly recommended for any product where you want to have a good quality. There are tools existing today from EDA vendors. They're quite expensive. In this case, you get something actually for free. Yeah.
Are you applying that to a specific ESA standard?
No, there is no ESA standard other than the fact that you should be able to exactly do exactly this.
Okay.
So, yeah. At least when we have done projects for ESA, then these are the tables they want to see.
They are evolving in terms of what they're doing. I just wonder whether there was something specific that you've seen from ESA.
No, I think this has been standard for quite a few years. So
yeah, there's new stuff coming out of ESA.
Yeah, and I know they're modifying the standard now. But I think they're still going to sort of require these things. Yeah. And this is lots of manual, boring labor. So you want this to be done automatically, definitely. And the good thing about this, and even better thing about this, is that most of the time they will require that you do this upfront before you make test cases. And in my head, that's really stupid. Because when you make test cases, then sometimes you see that it's much better to put that test case in together with these things, right? And that's then much easier to handle than later on, and this can generate all the tables you need, and I think ESA will be really happy with that. Okay, let's see. Yep. So, and then we did a second ESA project a couple of years ago, where we included enhanced randomization, optimized randomization, and functional coverage. I'll come back to each of those. Let's start with enhanced randomization, because we used to have in utility library, we have that since 2015, quite simple randomization, extremely simple in functionality, but also extremely simple to use. But now it's October 21. We included enhanced randomization, well integrated with UVVM, especially when it comes to alert handling and logging. Strong focus on overview and readability, because I think that's, as I said previously, that is the most important thing, both for making a design and making a test bench. So we have added keywords to ease the understanding. I'll come back to it in a moment. So standard approach here is randomization in one single command. And of course, if you do simple randomization, that is still that simple. So anyone will understand that this generates a random number between 0 and 18. It's obvious, right? But more complex randomization is often far more difficult to understand. But as I said, there are ways to improve this. So for instance, in this case, we say, I want to generate a random number between 0 and 18, excluding number 7. And then we put in exclude in there to actually show that we exclude that. And it's easy to understand. Everybody can read that and see exactly what happens. Or you want to add a couple of numbers as well. Or even worse, you want to add some and exclude some. And if we put this on a line of numbers, it's really difficult to understand what's happening. But in this case, you see immediately what's going on. And a similar readability for weighting, for instance. In this case, we put the order of the parameters into the name of the command. So it's doing a randomization, value first, weight afterwards. So 0 has a weight of 2, 1 has a weight of 3, and so on. So you immediately understand from the name what's going on. which is even more important if you have a range with the weight. Then you see the range comes first, weight afterwards. So 0 to 18 with a range of 4, and so on. So you can immediately see what's happening, and it's easy to read and understand this. So this is coding for readability. Of course, some people say, hey, there's more characters to write. Yes, that is correct. But typing code consumes an insignificant part of development. Totally insignificant. But reading and understanding, that's repeated over and over again, that's what is important. And that's why we added this add and exclude, because now it's easy to understand, easy to read. And you're going to read this lots and lots of times, you and other people. So investing in better code yields a huge return on investment. It is, of course, also easier to maintain and extend. So some other randomization features, I won't go through all of those, but I want to mention some special features. So for instance, one where you don't want to repeat any value until all the values have been used.
Yep, so sorry, one, ask question now or later. I had a simple comment in the previous slide if you don't mind. Yeah. So this is something that you could extend from the so-called AI and chat GPTs and things like that. One could imagine that we combine what you just said both. I mean, people have more things to type. They don't like it.
Yeah.
Let's say we take that code and then render this those so-called descriptive or elaborate version of the code. That shouldn't be that hard to do in a generative AI. You see what I'm saying? Let's say somebody types just my address ran.
Yep.
Without the added exe here, exclude. And then you, I'm not calling it a preprocessor, but just to put the AI in there. But something like a code generator could take that and render a better code. That way we get the best of both worlds, right? Yeah,
I'll give you sort of a frame that you can just fill in or whatever. Yeah.
Something like that.
Yeah.
So that's something we should
yeah, that could be done, yes. So I think that would be something that would be important for Sigasi or something who actually made any tools for that. Yeah.
Thank you.
So as I said, special features. If you don't want to repeat any value until you actually used all the values, then you just add the keyword cyclic, and you make sure that is what happened. Same thing if you're generating a vector of values. For instance, in this case, 64 values in the range between 0 and 255, and you don't want the same number to be repeated anytime. You just use the keyword unique, and you make sure that that's what happens. Because otherwise, most probably you are going to repeat one of those numbers when you have so many numbers. Functional coverage, as you probably know, is this user-defined metric that measures how much of the design specification has been exercised in verification, right? So it just checks whether various functional scenarios have actually been tested. So for instance, for UART, has the payload started with both 0 and 1? Has odd and even parity been tested? And also with the payload variation above, which means you have cross coverage basically between those. And same with baud rate, clock rates, and so on. This requires a manual process to set up everything. So it's complex, it's time consuming. But it's really great to check that the various specific scenarios that at least you have in your head have been verified. So let's look at a functional coverage example. So for instance, for a simple packet-oriented protocol, payload size of 2 to 256 bytes, destination address between 0 and 15. And of course, we cannot check every single payload size, at least not if it's sort of a more normal payload size of 1K, 2K, 4K, 64K, whatever. So we have to focus on important corner cases separately for payload size and all other aspects of that protocol and combinations of these. And of course, you want to focus also here on corner cases, in this case, value-related corner cases. So has the payload size been the minimum and the maximum, for instance, and something in between? And the same with the destination address. Also has selected combinations of these been tested as functional coverage. So for these, we define cover points for the things we want to check. And in UVM, a typical sequence will be this. You define a variable of a type called tCover point. This is a protected type in VHDL, allows you to use, or has provided with lots of different methods or procedures. In this case, then you add the bins, and for the bins here, you add for 0, 1, 255, and 256, and then for everything in between. And the syntax is quite simple, just add bin and the bin itself. And you tick off these bins as you transmit, you make your packets and transmit them. So for instance, I have a payload size of 2, then I tick off that in between, in the middle of the section there, and I send the packet, and I start with the next packet, and so on. And I continue sending packets until all my coverage targets are reached. Just a simple while loop. And UVM also has transition coverage. That means we can check that I checked in this case first a packet of 0 bytes, followed by one with 256 bytes, followed by one with 0 bytes again. That's also quite useful. And I mentioned bin generation here. I'm not going to go into details on that, but there's lots of different ways you can do that with legal bins, illegal bins, and so on. And also different ways of specifying that. I mentioned cross coverage. I won't go into that either, but it basically means that you are, in this case, for instance, checking combinations of the payload edges and the destination address edges. And there's the syntax for that. But by the way, the syntax is, of course, given in a proper documentation for UVM. You can find everything there. What I want to focus on is the functional coverage reports, because I think that's important. Because if you use system Verilog, for instance, I found it confusing to understand what the different coverage actually means. I'm going to show that in a moment. This shows a cover point for called PT1. That's a default name, unless you give it a different name. And then you can see all the different bins. And you can see you have 2 types of coverage. You have a bin coverage and hits coverage. And that's what I think is really nice here compared to what you get in other tools for system Verilog, for instance. So you can see here from the hit coverage that you can see there are 3 out of 5 on 100%. That's why you have a bin coverage of 60%. But of course, you have more hits in the bins that haven't been fully covered yet. So that means the hit coverage is actually higher. But now you can see the 2 different numbers separately. Gives you more information. And then you can have an overall coverage report for all your cover points with all the statistics for all these cover points. I mentioned optimized randomization. That's basically randomization without replacement. So if going back to university, then if you have a bucket of red and blue balls, in this case, you have a probability of picking a blue ball, that's 40%, right? And if with normal randomization, you would always have a 40% probability because you would put the ball back into the bucket and it would still be 40% the next time. But in this case, for optimized randomization, when the ball is out of the bucket, you don't put it back. So that means the next time you you select or pick a ball, the probability of picking a blue ball will be 25%. So it's weighted according to target distribution and the previous events. So that means for this protocol thing, it will yield the lowest number of randomizations for any given target because you don't repeat the things that you don't want to repeat. So it's a major reduction in number of packets in this case, and plus also simulation time. And of course, imagine if you have a payload of much more or lots more different types of bins, and you want to satisfy all the requirements, then most probably going to satisfy some of these requirements and others are going to be a major overshoot. With this, you don't have any overshoot. So are there going to be more ESA UVM projects? I'm getting that question a lot. So ESA is very committed to helping the European FPGA community. That's really good. And people talk a lot about system Verilog here. And there's the reasons for that. But in Europe, more than 80% of the FPGA community or FPGA designers are actually using VHDL. So a new ESA UVM project is planned and most probably will start in August and September. I can't say anything about it because we haven't really finished the agreement with ESA on exactly what to do. But it will be give even more functionality to UVVM. It's available on IEEE and also on GitHub, and people will see that there are several repos on GitHub. There's one default complete UVM. Then there's an extended UVM, UVM supplementary, and all the test cases that we use for regression tests are there. Apart from some test cases that we cannot give out because we use third-party IP in that test bench. Otherwise, you can see the test bench. There's also something called UVM Lite. People ask me about that. Why do we need that? It contains utility library, BFMs, randomization, functional coverage, all in one single library, in one single directory. And this is intended for newbies to VHDL that don't understand really how to handle multiple libraries and so on. It's not intended for people who knows how to, or sort of are experienced with VHDL. And there's also UVM GitHub.io, which is the documentation. It's currently a mix of HTML and all PDF files, but everything is there. So talk about this, this decreasing awareness and increasing problem down to the cycle rated corner cases. And what I want to say basically is that UVM covers all of these. I don't have the time to really go in detail on everything in 1 hour. I mentioned that 50% is used as development time is spent on verification. I asked, could verification time be reduced without reducing quality? I think definitely so. If you look at the efficiency here on where time is spent on verification, again, I think we can definitely be more efficient by doing things more structured. And if you look at that, I would say that we have a huge improvement potential. So if you assume a 6,000-hour project, then that would be 3,000 hours spent on verification. And I would think that you can spend a lot of time on debugging, test planning, test bench development, and on creating tests and on simulation. And you can see that on the debug part, I think that's the really most potent potential for reducing the development time. And if you add that together, I think a 50% improvement, in this case, giving you 1,500 hours saved, is possible in many cases. But it, of course, totally depends on the maturity in the company doing verification. But in many companies, I think this is actually a relevant and realistic improvement potential. We do courses on both FPGA design, actually, and verification. And you can find that on our website. Won't go into detail on that. And just to conclude, sort of a UVM in a nutshell, I think there's a huge improvement potential for more structured FPGA verification. Talked about this. UVM targets all of these things that I think are extremely important to enable both quality and efficiency improvement. And it is all open source, including the verification components, including everything. It has the largest collection of interface models, BFMs, and verification components. We work together with ESA to extend the functionality. It's available on GitHub and IEEE. It runs on any VHDL 2008 compatible simulator. And I think as a result of this, UVM, the usage has been exploding. It's the fastest growing FPGA verification methodology of all. It's growing faster than System Verilog over the last few years. And I think you have a huge saving potential using that on simple projects, medium complex projects, and even more, of course, on a large project. At the same time, improve also time to market mean time between failure, and life cycle cost. And that's it. Any questions? Yes.
So you mentioned about the extending the VVCs, right? So I come from more, I mean, I speak both the languages, system builder than VHDL, but more SV, to be honest. So given the class-based stuff, the extension is quite natural, or at least the AOP or the OOP. Again, I've done a lot of specman, I still do. In those cases, it's easy to extend.
Yeah.
In VHDL, so far what I have seen, it's not that intuitive to extend things. How do you really, could you please, I mean,
Yeah, it's a good question. It's definitely different from system Verilog. I mean, VHDL is not object-oriented, it's component-oriented, right?
it's not AOP either. It's not
Yeah. But that's exactly why the architecture is so important. Because if you have, in most test cases I've seen, the architecture is pure horror. So that's why we have focused on making an architecture with clearly defined blocks like interpreter, queue, and executor, and so on, because then it's easy to add the same type of structure and to control everything from that structure. It's easy to add another checker by just including another command in interpreter, for instance.
So you have to touch that. I'm sorry to go in there, but let's say I have an APV 2.0 VC. You probably have an AMBA, right? You have an APV.
Yeah.
Let's say I want to add an APV 5.0. Just APV 5.0, which is a new standard from AMBA. And it does add only one additional signal. Let's assume for the namesake.
Yeah.
Okay. To my limited knowledge of the VHDL today, you cannot just extend it. You got to kind of copy it.
Yeah.
Add the stuff.
Yeah.
There's no other.
But then you're not talking about the verification components. Then you're basically talking about the BFM. The bus
It's terminology thing, but yeah.
Yeah. So, but the BFM, you have to make that BFM or bus functional model anyway, right? And of course, VHDL is different from system Verilog, but at least in VHDL, you always have to make that BFM for any type of interface. And everything in UVM, basically, I talked about now with the verification components, comes on top of that. So once you make the change in your BFM, there's basically no change to verification components. Yeah.
So 2 points. We've been supporting FPGAs for many, many years. And what we were originally called an FPGA is not really what an FPGA is today. Because the granularity is going up in terms of the basic building blocks that you've actually got available to you. We've seen people putting up charts about, the number of verification engineers, not enough verification engineers. The same is actually true of people designing in Verilog and VHDL, such that the FPGA vendors are thinking about, well, how do we get more people using this? So they're pushing everything up the food chain to say, let's start thinking about doing designs in C. Let's do the verification and the simulation at the C level before we even get to gates, and going straight from C to gates, and hopefully getting rid of most of the bugs through that process.
Yeah.
So how would all of this, if you fit into more of an automated type system design environment, to actually then come out with a UVM sort of classified test harness without having to rewrite it if you're coming from that C-level source?
Yeah. Okay. So first of all, if you look at the time you need to spend making a test bench using UVVM, in some cases you can just use verification components already available. If that's all you need, you basically it's Lego-like. You just put verification components, connect them to your the test, and everything is ready to run. Because you don't need any connection, for instance, from the verification components to the test sequencer, because they're globally connected. And that means you can immediately start, not immediately, but very soon you can start writing test sequences. And those test sequences, as I said, they can actually be written by software designers. They look like any procedures that you make in C. They don't look at C, but it's basically a procedure with parameters. And any software designer can read the manual and see, yes, I'm going to use that procedure to do an axis stream. I'm going to put my array of data in there, and so on. And it's really dead simple for anyone who is not an expert on VHDL or FPGA.
But there's still a break in the flow.
Sorry?
There's still a break in the flow. You know, if I'm doing my system level design at the C level, I'm debugging at the C level.
Yeah.
And I can go from C to gates for my FPGA. That test bench still has to be rewritten and modified halfway through that flow, which then breaks that test methodology structure. You see, the bug could be introduced between going from the C level simulation to the UVM model.
Yeah.
How do we?
There's no sort of automatic way from a C test bench to a UVM test
Do we
bench.
see that there is a need for that? Do you see there's a need for that?
I can always say there is a need for at least some kind of improvement here, but I think to go from a pure C test bench down to a test bench for this FPGA, in my head, I don't think we are going to have a solution for that in quite a few years yet. And I think this is a very good intermediate solution if we're ever going to go there, because you can use the software designers to make that code. And you can also write or wrap those procedures and functions into higher level procedures as well. That might be equal for software and FPGA.
I think there is a perception there's going to be an exponential growth of FPGA design being done at C level over the next 5 years or whatever. So it's going to be interesting.
Yeah, I can also mention one other thing as well, because if you have, for instance, a built-in CPU in your FPGA, then what we have seen, or what we could do, is then to have a built-in verification component rather than using the actual software, because you're going to be able to use that anyway in a VHDL test bench. Then you can put in a verification component inside your design as a replacement for your CPU that basically takes over the control of the internal bus, and you can control that from the external test bench.
But that's just a BFM.
It's a BFM, yes, but you have access to it from the external test sequencer directly into the system.
Okay.
Because it's globally connected, you can put that anywhere deep inside your design. Any other questions?
Do you see a need for a testbench linter in UVVM? I mean, not necessarily for the library itself, but for the end users. You want to set up, like ESA you mentioned, they had a rule deck for lint, not here.
It would
be a similar thing for.
It will definitely be nice with a linter, yes.
Would you like the spec for it? Would you, let's say, collaboratively, is there a way to come up with a set of rules to be verified in a typical UVVM test bench? Then it's easy to go ahead into the implementation side of it, because you probably know system radar and UVM have been evolving over many, many years. And we have now rules, and now the linters are coming into place. So it'll be good, nice to see the UVVM defining certain rules, saying this is what UVVM compliance really means. Right? Then it's the next step to go and start implementing those rules in some way or the other.
Yeah, I think that could be done. We are definitely not going to spend time on that, because first of all, we are not experts on writing linters, and we want to focus on UVM. But to actually cooperate with someone who wants to do that, that's...
So we are interested. But my goal will be to come up with a set of rules. That's I would say the challenge. Challenge as in anybody can do anything, but it's just a matter of time. And you guys are the experts, are the UVVM side of it. And you could say that, okay, at least do these naming checks are easy, right? So it's okay. It's not something that I'm so keen on, but something a little bit more fancier. Right.
Syntax.
Syntax. Again, a compiler would check. I'm really looking for something a lot more. For example, if you speak to somebody else, I would go and say, if you have a driver, UVM driver, you should have a virtual interface. If you had a UVM monitor, you should have a virtual interface. Just so any other component is banned to have a virtual interface. This is, I'm sorry, I'm throwing system it up to you, but But from your side, if you say, okay, here is your executor transponder,
Yeah, we have a slightly different
different terminology,
yeah.
but let's say the executor cannot have a semaphore or whatever, right? Something.
Yeah.
If those kind of really meaty rules are in there, that's when it gets interesting.
Yeah.
Otherwise,
Okay. Yeah.
checking for syntax, okay. Checking for naming, it shall be named A underscore. Fine, fair enough. I'm not behind those. I'm looking for real good stuff.
Yeah.
So if you're interested in collaborating, I'll be very keen.
Yeah, we could definitely discuss it. Yes.
Thank you.
Yeah. I mean, we are really open to anyone who wants to contribute to UVM. It's free, it's open source, and even if someone wants to make some commercial solutions around that, that's fine because it increases the total availability of the complete system. Any other questions? Okay, thank you.